All right, for our last reaction today, we're going to do something called hydroboration. And then we're going to follow that with a reaction called oxidation. And I see here that the groups are on the same side. Yeah. The stereoselectivity is called sin when the two new groups are on the same. Well, this morning's was a ring. You didn't have a ring of the skeleton. Type it. And looks like it needs to be times New Roman. Maybe about a 20-point font. There you go. And everything moves. Okay. And over here, I want to remind you again, you got B is 2.0 and H is 2.1. What are those numbers again? Electronegativity, which means the more electronegative H we don't usually say that, do we? It's almost always the opposite if H is involved. Like HBr, HCl, HI, H2O. Always less electronegative H, right? But here we found an element that's even less electronegative than H. So it's Markovnikov right now because it ended up on the more substituted carbon. And I'm going to bring this up right now. At the end, you have an anti-Markovnikov. Alcohol. Isn't that OH on the less substituted carbon? The more electronegative O is on the less substituted carbon. That's the opposite of Markovnikov. Okay. So how did this happen? I thought alkenes can only do Markovnikov. Well, that story didn't change. When it was an alkene, it did a Markovnikov reaction. And then we did a whole new reaction to get rid of the boron and replace it with a hydroxyl. Right? You look at it. I got rid of the boron and replaced it with a hydroxyl. So we tricked the alkene by doing it in steps. So we gotta do this reaction. Hydroboration. What's a 3-methylpentyl group? It's right here. And the 2 is where it's attached, right? Carbon number 2. Okay. So really, how many of those groups are on the boron? 3. I drew it once, and I used the R for the other 2. So it's BR3, right? Equals BR3. Do not put a lowercase r there by mistake. That would be total nonsense. If you put a lowercase r, that's bromine, right? There's no bromine on this page at all. Boron. Okay. Hydroboration mechanism is the easiest mechanism of the semester, and the oxidation on the bottom of the screen is the longest mechanism of your semester. The oxidation, the longest one, is also one of the better done mechanisms for the class as a whole. And you're wondering, how can it be the longest mechanism and be one of the better done ones? Because I promise you it's on your test, and then the next test as well, so you know what's going to happen. And 2, I've got a lot of, even though it's multiple steps, I've got a lot of little patterns inside those steps that should help you remember what's next. So wait for that, okay? We'll go step-by-step patterns that you're looking for, trends that happen. Got it? Hydroboration is a piece of cake. What happens is the pi attacks the less electronegative boron. So let's say that again. The pi attacks the less electronegative boron. I just put it on top for fun. And then you're going to have 4 bonds to boron, right? Reminder, what's the charge on boron when it has 4 bonds? Thank you. Previous page, sadly blank. I have a new page by mistake. Right here, boron with 4 bonds, negative, right? And what happens when it loses one of the bonds? Well, it comes back to boron neutral. In a nutshell, that's boron's chemistry. Alternating between 4, 3, 4, 3, 4, 3, like a little machine. That's its nature. If you remember one thing about boron forever, it's that. It likes to alternate between 4 bonds and 3 bonds, and then 4, and then 3, and then 4. Okay, and there's that mystery blank page, which I want to get rid of right now. And so what we did was we made a 4th bond. The boron would be negative after this, right? And you know what hydrogen thinks about that? Well, what did hydrogen think when boron had 4 bonds? What's its nature? Is to lose one of those bonds, right? Well, we don't even have to wait for the boron to be negative in this one. One of these H's sees boron becoming negative and says, no, I'm more electronegative. I'm going to take these electrons. I'm going to go to the carbon that's a better cation. And you never get to be negative, not on my watch. Hydrogen's getting pretty militant here, I know. So it's going to take its electrons and go to the carbon that would be a better cation. Tell me which of these 2 carbons is a better cation? The one on the right? Yeah, because it's tertiary. It's got more hyperconjugation. So you never see the boron anion. And the H comes to the more substituted carbon, and no surprise, look at the product. And when both bonds happen at the same time, here's an outside comment. Both bonds occur at the same time. It was supposed to be an M followed by an E equals thin. There's a very good reason. Here's an alkene, flat alkene right there. Your BH3 can come in from the top, in which case both bonds would be wedges, or it can come in from the bottom, in which case both bonds would be dashed. You cannot have BH3 simultaneously up here and the same BH3 down there. I don't have to explain that, right? You can't be in 2 places at one time. So you can never have one wedge, one dash, because BH3 is all in one spot, either above, which would be this case, or 50% of the product would be dash dash. You don't have to show me both products. Okay. And that's not even the end of the story. It makes a species that's not exactly that one I drew. It's this one. Do you agree? And you're going to repeat the mechanism. You're not going to do it ever. Repeat with another alkene. Should be black. And then another alkene. And the reactions get faster and faster. You know why? The first time is the slowest. The next time is faster. And you're going to replace this H with another one of these groups. Tell me why it's faster with this species than it was with BH3. The thing that speeds up or slows down the reaction is how fast this arrow happens. Why is it going to be faster for this arrow when the pi attacks the boron down here? Here's the answer. Let's see who can figure out what I'm trying to say. The answer is here. Yes, in my explanation, which doesn't always involve words, size does matter. What am I trying to say with the sizes? Why is one bigger? Do you think it's less positive than the one above it? He said sarcastically. No, I put it there because it's more positive. You need to tell me why it's more positive, this boron, than the original boron. Yes, you can look at the periodic table now. Yes, you should say 2.5 replaced 2.1 here. You got a carbon, 2.5. You had a hydrogen, 2.1. Boron's going to be more positive with a 2.5. Carbon pulls pulls the electrons in the bond more strongly than does hydrogen. This second reaction's faster, and the third one, because there's going to be two bonds to carbon, is going to be the fastest. And you never show me the mechanism twice, so on the test, I do it this way. Tests. You'll have just one H on the B. You cannot mess up. I will have two of the groups already on the boron for you. You show me the third one. Attack the B, and these electrons come back to which carbon? More substituted carbon. So on test, you're going to do that, and that's all you're going to do, and done. It's the same mechanism as before, isn't it? Yeah. So two arrow mechanism, that's it. Simplest mechanism of the semester. No intermediate. You don't have to draw me any molecule. I will have these two drawn for you already. You give me the two arrows. Got it? Just like the next part, I will have these molecules drawn already. And it looks like we're just doing the first reaction. And it's going to happen 3 times. A little misleading here. I should have done it this way. One of those. 2. Oh, it straightened it for me. 2 more H2O2. 2 more HO negative. You get 2 more of these, and you get this called borate. That's the real story. Okay, so this happens 3 times is what I'm trying to say. And similarly, each progressive one is faster than the previous. I'm going to tell you the things you should be looking for, the patterns. I'll go slow. And I'll summarize them as I go. 6 steps. That's one thing you should try to keep track of. Step 1 and 6. I'm going to give you another chance, everybody. What is the type of reaction where a proton moves from one species to another? Step 1 and 6 are both acid-base. That's one of the patterns. I'll be adding to this list. You don't ever have to write down the patterns. You just show me you know them by doing the mechanism correctly, okay? So, of these 3 chemicals, do you see either a strong acid or a strong base? Because that tells you where to start. I see a strong base. Please react that first. And which proton do you think is the most reactive one? I even gave you a hint by drawing it sticking off. Which proton is the most acidic, do you think? I'm going to go towards the blue one to try to throw you off. The blue one has a pKa of 50. If H is bonded to O, it's closer to 17. I gave you the answer. 17 is going to react much faster than anything else. And I know it's not water, but it's pretty darn close in terms of pKa. Peroxide's not much of a different acid strength than water. So step one, let's number these. Acid base, as promised, you get H2O. You don't need H2O, but you do need this. And I'll put it in purple. So we'll just keep adding dots here. The first 2 times you make OH negative, you attack B with it in the next step. Okay? The first 2 times you make O negative. It's more general. Oh, too big. O negative. It doesn't have to be OH negative. We made OH negative right away. It's not the same. Just any O negative that you make. Okay, so tell me what the next step is. I put the words down, you convert it to a mechanism. So where's your arrow start and where's it end? You got to start your arrow at a pair of electrons and B doesn't have any. The long pair on the O minus that you just made attacks what atom? Please just read. The B. There's your arrow. Attack B. Boron. Okay, that's step 2. Number these steps. Gotta get to 6. I'm going to lose my colors. And there's a 4th bond from B to OOH. What is B's charge when you have 4 bonds to it? Minus. Here's your next dot. The dots are the patterns you're looking for. They're kind of randomly written everywhere, huh? But the dots are how, the things you have to remember. So green, we'll do a black dot. Black dot. B alternates formal charge. It goes from 0 to -1 to 0 to -1 to 0, and I like to think of it as a graph, because basically you're graphing a 0 and a -1. You get to do a W, and I like that, right? That's a W. Come on, your teacher's name is Whitaker. Okay, so we're down here, aren't we? Next reaction, guess where you're going back? 0. Next reaction, guess where you're going? -1. And the last time you change formal charge is this one. You go back to 0, right? Okay. That's helpful, isn't it? And then what's going to happen is This thing is an unhappy camper. The main reason is it's got peroxide in it, and peroxide has this thing here, where you have an atom that has lone pairs next to another atom with lone pairs. Any species in chemistry where you have atom with lone pair or pairs, next to another atom with lone pair or pairs, it's called lone pair repulsion, and it means you want to break that bond because it's not a good thing. So that's why there's disinfectants like hydrogen peroxide and even iodine, I2. You ever had the doctor take the purple stuff, put it on there before they cut into you with a knife? If you haven't, well, bless you. You haven't had to have an operation. But yeah, the purple stuff is a great disinfectant because iodine's bonded to iodine. Lone pair repulsion. It'll do anything to break that bond. And here, what's going to happen is carbon is attached to boron. What's carbon's electronegativity? 2.5, and it's looking at a boron that's minus. Carbon's saying, if anybody's going to be a minus in here at this job, it's me, right? I'm more electronegative than you. You can't have a minus charge, not on my watch. A lot of people like talking to boron like this, don't they? Hydrogen was talking to boron like this earlier. Okay? And what happens is this is like moving from one atom to the next. We have a name for that. That's a rearrangement. Yeah. And you're going to make what other species with that second arrow? What's the name of the species? Say it again. OH minus, what's its name? Hydroxide. And more important, what's the charge on the oxygen? And this is the second time you have made an O minus. So you already know the next step. As soon as you write this, you know the next step. The first two times you make O minus. What do you do with it? Attack B with it in the next step. Well, you better draw what else is occurring, and it's in black. And I'm going to skip that black H because I never needed it. The bond is now over here. Still a wedge, but this time it's to the purple O, which is still bonded to the B, which has two R groups on it. Hey, 3 bonds for B. What's your charge when you're 3 bonds on B? Yeah, shake your head, good answer. No charge. And that was step 3. And you already know what to do. In the second time you made an O minus, you do the same thing that you did the first time you made an O minus, and you did what with this O minus? Attack what? Attack the B. This time it's this B. This B. Making a 4th bond to B. Guess what its charge is going to be in after step 4? Minus, and you're almost finished with the charge thing, aren't you? Because you're down at your second W here, part of your W. And what do we got? And let's make it a little neater. Purple O, bonded to B, 2 R's, and I made the OH green this time. What about boron with 4 bonds? What's the charge? Beautiful. And then, in step 4, you put on an O. In step 5, take off the other O. It's an oxygen exchange, steps 4 and 4 and 5. Oxygen exchange, 4 and 5. There's a new O minus. Setting up step 6, which is what type of reaction? Acid base. B is finally neutral for the last time. It's bonded to O, bonded to H, and the other species is this purple O with a minus. And I think you can see how these two become this two, these two, R2BO minus, R2BOH, there's your proton. Carbon OH from carbon O minus, there's your base. It's a big, strong base. Step 6, acid base as promised, done. Step 6, need arrows. I don't want to trample on my notes. Here, separate them out with a yellow box or yellow squiggles. It's one of our dots. And then step 6, underneath, above, which one's best? I think that does it best. Step 6. There's a lot to this thing, you got to admit it. And right now you're saying, I don't know what he's talking about. Everybody does okay on this mechanism. I couldn't do this. You got to practice it multiple times. Never even think you can study mechanisms by looking at them. It doesn't work that way. You just can't explain to somebody the actual mechanical action of you hand on paper is part of the process. You putting it down based on an original, and don't base it on this original. Okay. Here's something. This morning's video went off the rails because I thought I stopped the video at this point right here. And then I kept talking for 6 more minutes. And you have no idea what I was talking about. You're not seeing any. What I did was I told the students how they could do their journal for the semester. Okay. So here's the deal. I'm going to do it so you can see what I'm doing this time. All right. Journal for the semester. Stop. Okay. Now I need to go and find this one. Create a new, I got my portal. I believe I sent it to you in an email. This is where things get dangerous, everybody. I can't have you look at my email. I sent you chapter 6 in an email, right? Or a link to it. I didn't? Nobody reminded me that they didn't have access to the textbook. Yeah, that was a sad story. It was that email, yeah. I believe it was Friday. And I'm just going to turn off the screen for a second and hopefully remember to get it back on. Okay. So yeah, you're not seeing any of that on the video. So the video is kind of off the rails again. You're not watching what I'm doing. That's good news. And I'm just going to go to Friday's sent messages. Sent. 5, 4, 3, 2, 1. Monday. That's a lot of Mondays. Friday, yeah. 41. Great entry. Gosh, I found it quick this morning. Okay, winter classes. Sorry, it's not happening like I thought. Here are links to chapters 5 and 6, finally. Wow, it was torture. What's going on here? It is open. Okay. I'm going to do a stop share on the screen because I believe it might not know where I am. Sharing again. I got the textbook open somewhere. Yeah, there's the email. I clicked on this link for chapter 6 and there it is. I'm just not thinking that'll be on the screen now. Just in case. Ooh. Oops. Cancel. Yeah. Share screen. There it is. So you want to do your journal for the whole semester. It's so easy. You go to a section until you find a shadow box. There it is. You copy the title, which is in the textbook. It's right there. Copy that. Copy the whole shadow box. Done. That's 6.1a. Done. If you want, you can copy more examples. There's another 6.1 mechanism in a shadow box later. Somewhere. There. You can copy it, but you don't have to. I just need one example for each mechanism, okay? And then you go on. 6.1b. There's the title. Copy it. There's the shadow box. Copy it. You can do the whole semester tonight. I emailed you chapters 3, 4, 5, and 6 on that last Friday at a time. I don't know the time because I realized a student had sent me an email that said, is this pKa table okay? And it was clear she got it from a different source for a good reason. Nobody had access to the textbook. If you bought it from the bookstore, you have the right book. But the book, they didn't have a lot of them, right? So a lot of people just went with what they thought was the ebook. If you've been using the Brownfoot-Iverson book, which does come with Moodle, etc., it's a good book, but it wasn't written by me for you to answer my test question. Yeah, if you have friends and old relatives, etc., you probably got a copy of the book, or you had access. It didn't work for me and a lot of other people, so you were cool. You knew how to get to the book. They don't even know exactly what went wrong yet. This is a sticky one for Cengage. They have never taken this long to fix something. Something goofy happened. Anyway, it's all in video. Sorry, we're going on and on about it. You're going to have the book. You've got chapters 3, 4, 5, 6 waiting for you in your email. 6 is where the mechanisms start. Do what I just showed you now. And 7, either will have access to the book by the end of this week, or I will email you chapter 7 and 8, okay, if they can't get this textbook thing figured out. Okay? And that's that. Oh, one final comment. Occasionally, you'll see a mechanism that's not shadowed. But please tell me you know there's a mechanism in here and tell me how. There's a kind of arrow there that is not normal arrow. Curved arrows are mechanisms, right? And that is the title of one of our mechanisms on the list of mechanisms, carbocation rearrangement. And if you copied what I told you in the lecture notes, you were fine. Because it looked a lot like this, right? Do you remember copying it? Yeah, there's like 5 examples of carbocation rearrangement. You could have copied these. I think only 2 times did I forget to shadow some mechanisms. This was one of them, okay? But it's got the title and curved arrows, you know it's a mechanism, okay? Other times, it's just always shadows. Hey, this is a carbocation rearrangement mechanism because it's in this section. Why don't you copy that title and this shadow box? There, done. It's got a, what kind of shift happened here? A hydrogen shift. Yeah. Or copy this one, it's got more shifts. I don't know. And there's the one we did earlier, the other day with a shadow box. And here is the one we did today. Mercury one is coming up there. Mercury one, yeah. Look familiar? Hydroboration's coming up. A lot of connecting with chemistry stuff. We don't do that. That's just personal interest stuff. And we have hydroboration, 6.2. That's where we finished today, right? There's your hydroboration, smallest box of the semester. Here's your oxidation, one of your biggest boxes of the semester, right there. And there you go. We're going to pick up on Monday with 6.3. That means we're going to finish chapter 6 on Monday, moving on to chapter 7, maybe the end of Monday or beginning of Wednesday. Okay? And that's all I have for you today. I believe I just got